Okay, so it is a great pleasure to introduce Lai-Sang Young, that will talk about dynamical systems here. She's got a lot of prizes and awards, and let me just mention that recently she was elected as a member of the National Academy of Sciences, and she got this Jürgen Moser Lecture Prize for your deep contributions to the theory of non-uniformly hyperbolic dynamical systems. And today she will talk about observable events and typical trajectories in finite and infinite dimensional dynamical systems. So, Lai-Sang, please.
Thank you. Thank you for having me speak in this conference. Now, this is a talk in dynamical systems, and what constitutes an observable event or typical trajectory obviously has to do with context. And I don't mean to be proposing anything universal. What I'm going to be proposing is a particular notion of observable event and typical trajectory. Okay. And so I'm going to start with finite dimensional dynamical systems, to which I will add noise, and then I will go to infinite dimension and talk about how the same concepts that we see in finite dimension will fare in a noisy setting and in the setting of infinite dimensions. Okay. So the first part of the talk is finite dimensional deterministic dynamical systems, and the phase space is either RD, or finite dimensional, or finite dimensional manifold. And I'm thinking about differentiable maps that are invertible for simplicity, and or the inverse is also differentiable. Now, on RD, or a Riemannian manifold, there is a measure class that stands out. So little m is going to denote Lebesgue or Riemannian measure in my talk throughout. And in finite dimensional dynamics, one often takes the view that observable events are described by positive Lebesgue measure sets. So throughout, I'm going to equate the two, observability with positive Lebesgue measure sets, for as long as I'm in finite dimension. And I have a notion of Lebesgue or Riemannian measure. The setting that I'm interested in is very simple. So here's an open set U that gets mapped into itself. So it gets squeezed inside of itself. And once it's squeezed inside of itself once, if you keep iterating, it will get smaller and smaller. I take the intersection, and I'm going to call that an attractor. Now, in this setting, there is a kind of ideal dynamical picture. I'm not saying the things that I've written here in this yellow box are not necessarily true, but it's the picture that one would hope for as being typical, the typical picture. So let's describe this picture to you. So in this picture, if you look at Lebesgue measure and use the dynamics to transport the measure forward, it converges to something. And if it converges to something, then that something is necessarily an invariant measure. Okay, so that's the first point, that if I transport the Lebesgue measure forward, it will converge to something. And the second point is that if I then look at the largest Lyapunov exponent, i.e. the growth rate of the norm of the derivative of the nth iterate, okay, I'm going to denote that by lambda max, okay, then if the norms continue, so lambda max positive means that it grows exponentially, negative means it shrinks exponentially. So in the case where lambda max is less than 0, one can imagine that there's a lot of contraction in the system, and one can, and in this picture, mu would be supported on a sink. And if lambda max is positive, then mu is supported on an SRB measure. And I'm going to have to tell you what an SRB measure is. Okay. So this is the picture that you transport the Lebesgue measure forward, you get to an invariant measure, and then you look at the Lyapunov exponent. If it's contracting, it sits on a sink. If it's positive, then it sits on a special invariant measure that sits on attractors, which I'm now going to tell you about. Okay. So what are SRB measures? SRB measures are, to dissipative chaotic systems, what Liouville measure is to Hamiltonian systems. So in Hamiltonian system, since we care about Lebesgue measure for Hamiltonian system, obviously Liouville measure is the measure that we care about. But now think about the situation of an attractor and think about it as volume decreasing. If it's volume decreasing, then by definition, there can be no invariant density because the measure is going to be supported on a singular measure 0 set. Now, in this setting, the in the case of, let's think of it as volume decreasing system, and when the lambda max is positive, then there an invariant measure nu is called SRB if, okay, first of all, the Lyapunov exponent has to be positive, nu almost everywhere, and the conditional measures on unstable manifolds have densities. So what this says is that, okay, volume is decreasing, there can, any invariant measure is necessarily singular, but it can still be smooth. It can still be smooth in the unstable directions. So if you look in the stable directions, it's singular, but if you look in the unstable directions, it has a density. Okay. So SRB measures, SRB stands for Sinai, Rouault, and Bowen, and it was first constructed for MCA attractors in the 1970s. Some of the ideas for MCA attractors were extended to general dynamical systems by Le Drapier and myself. So the idea of SRB measures is now much more general, but it doesn't mean they necessarily exist. Okay, so let me try to explain why, if you push forward Lebesgue, that one should expect it to go to an SRB measure when there are some expanding directions. Lambda max positive, the growth in the norm simply means that there are some expanding directions. Well, take a piece of the phase space, map it forward. So let's say it stretches in some direction and contracts in others. So you keep mapping it. So suppose it keeps stretching in this direction and keeps contracting in the transversal direction. So what happens is that in the limit, it's going to align with something that's smooth. The map keeps smoothing in these expanding directions. So it's going to, in the limit, it's going to align with something that is smooth. And therefore, that's an SRB measure. Okay, so why are SRB measures important? Okay, they are important because they are visible. That is the whole point of looking at them. Okay, so a point in the phase space is called future generic with respect to an SRB measure. If its future orbit is described by this time average as the n goes to infinity, is described by the measure. So in other words, a phase point is future generic with respect to an invariant measure if its orbit, if the large time distribution of its future orbit is described by the measure. That's what it means for the point to be future generic. So here's the theorem. The last step was proved by Pugh and Xu around 1990, and it's building on the work of many other people. Is that if you have an ergodic SRB measure with no zero Lyapunov exponents, then the set of future generic points has positive Lebesgue measure. Now, because we care about positive Lebesgue measure, that's the same as observability. That means that this measure itself is observable. So this is the first point that I would like to be clear about. We care about positive Lebesgue measure sets. In the case of attractors, invariant measures cannot possibly have densities, but it doesn't mean that they cannot be observable. Even though the measures nu itself may be singular, the set of points described by nu still has positive Lebesgue measure, and in that sense, nu is an observable measure. I can even sketch a little proof for this result. So suppose that these are the unstable directions, WU unstable, and these are the stable directions. Okay. Now, if the measure is SRB, that means that if you look in one of these curves, Lebesgue almost every point is described by nu in the future iterates. If this point here is described by nu, then the entire stable manifold is also described by nu because they have the same future. Okay, so in other words, if Lebesgue almost every point here is described by nu, then you can integrate out, and if the foliation is nice enough, then that whole area, Lebesgue, two-dimensional Lebesgue almost everywhere, is described by nu, and so nu is visible because you can see Lebesgue almost every point. And this is the idea of the proof. And this property called absolute continuity of stable foliation is something I'm going to come back to. So I'm going to leave it for now. Okay. So let me review this picture. In the case of finite dimensional systems, there's a picture that we all hope would be true all the time. Is that if you push forward Lebesgue, you get to an invariant measure, and if you look at the Lyapunov exponents that you get, then if it's negative, that means that this measure sits on a sink. If it's positive, So there's a lot of derivative growth. Then this measure sits on and it's an SRB measure, meaning that even though it has no invariant density, it actually has a density in its unstable directions. Now, this picture is in fact true for XMA attractors. XMA was introduced by Smale in the 1960s, and this picture was proved by Ruel in the 70s. XMA just means that you have uniform expansion and contraction everywhere. It's a special kind of dynamical systems. Unfortunately, it's not true in general. For example, when you push forward Lebesgue, it need not converge. So many things can happen. The limit may fracture into bits, as in the case, very well-known instance of this is Newhouse's infinitely many sinks, okay? Or it may converge to something, but that something is not an SRB measure. And this picture, which is called a figure 8 attractor, is a typical example of that. You push forward Lebesgue and the attractor is the figure 8, but the only place that the measure can sit is this one point. Okay, it cannot support any measure on the figure 8 except for this one point. Okay, so dynamical systems in general are messy. It's not as simple as this even, and so with all this messiness, this picture is not always true, and a number of things that can go wrong is actually quite a few. Okay, and the thing is that even when it's true, it's very hard to prove because you have to deal with some complicated cancellation problems that sometimes it expands, sometimes it contracts. So there are complicated issues that one has to deal with. And there are not that many examples of SRB measures. So this is the picture for finite dimensional deterministic that I would like to convey to you. It's a very nice picture. Unfortunately, things are messier than we would like. And it's really not so clear how often it's true. People think it's actually true quite often, but it's not clear how often it's true. And even it's true, it's very hard to prove. Maybe I could stop to take a couple questions if there are any. This is the end of the first little bit. Are there questions?
It doesn't seem so. There are no questions here.
Okay, then let me go on to the next part. Okay, so now I'm going to go to random dynamical system. And I'm going to define a random dynamical system. There are many ways to define random dynamical systems, and this is a definition I'm going to use. Okay, so fix a phase space M, a space of self maps of M. So for example, from CR maps from M to itself, and fix a Borel measure on the space of maps. Okay? Then a random dynamical system is a composition of the form. You just take IIDs, you just draw IID with respect to new, and compose them, these random maps. Okay, so it's not picking a random map and iterating it, but instead it's drawing an ID sequence of random maps and composing them. You can of course do it in 2-dimension, in the two-sided. Instead of just going forward, you can think of it as coming from time minus infinity. And I'm going to use notation Fn omega. Omega bar denotes the sequence of omega, and Fn omega is the composition of the first n. So now if this sounds a little bit artificial to you, an important example is the stochastic flow of diffeomorphisms generated by SDEs. So if you write down an SDE with, this is the Brownian, standard Brownian noise, then it has been proved by a number of authors in the 80s that for almost every realization of Brownian path, this omega here is actually the omega bar over there. There's a one parameter family of diffeomorphisms or flow maps that satisfy the flow assumption where sigma s is shift. So in other words, this is exactly the same situation as the flow generated by an ODE, except that it's dependent on omega and it's time dependent. It's actually omega dependent. Okay. So the setting that I have introduced here is not so artificial. It happens in SDEs. Okay. Now there are two notions of invariant measures. One is a stationary measure in the sense of averages. So if you take a measure and you transform it with all of the maps, and then it doesn't take an average over all the realizations of the noise, and then it doesn't change, it's stationary. But the view that interests me more is pathwise viewpoint. And a pathwise viewpoint is that you fix for mu as above. I'm going to I'm going to take a sequence of realizations, a sample path, okay? And I'm going to take mu omega, be mu, actually it depends only on the past, so I'm going to write omega minus, be mu conditioned on the past. And these are called sample measures. Okay? So instead of looking at the average invariant measure, I look at the invariant measure conditioned on the past of a realization. So what is the meaning of that? Is the first thing to realize is that these measures, which are called sample measures, that because they are conditioned on sample paths, they are invariant. Okay, so if you use f omega sub 0 to push forward this one, then it's the same as the sample measure corresponding to the push forward of the path. And another important fact, and it's nothing more than martingale convergence, is that because it's conditioned on the past, you can go back n steps. So if I want to know, so you go back n steps and you start to use it, you start to push the measure forward from time minus n all the way to time 0. Okay, and then you let n get farther and farther. In other words, you go back in history, and so let's say you have recorded history for 200 years. Then you go back 200 years in time, and before that you have no record of anything. So the only thing you can do is to pretend that is the average, right? Since there's no information, you use the average. Then you look at what happened given starting from this average measure 200 years ago. What does it look like now? And as the 200 goes to infinity, what you get are these sample measures. Okay, so why am I talking about this? Is that these mu omegas describe what one sees at time 0, given that the transformation, the history has already occurred. Okay, so conflating mu, the average of these measures, which are often smooth, often have a density. If I pretend that this was Lebesgue, this is almost exactly the natural invariant measure we had hoped for in the limit when we, for the deterministic dynamical system, when we push Lebesgue forward. It's not quite Lebesgue. This is the average measure of mu, but it often has a density and often looks like Lebesgue. Okay, so in the deterministic case, pushing this forward doesn't necessarily give us anything, but in the random case, just because of martingale convergence, we know that if we push forward mu, we get it for free. That there is, and the limit are these sample measures. So we get part of that picture for free in some ways. Okay. Now, I also want to mention that the pathwise notions of Lyapunov exponent, in this pathwise notion, one could think about Lyapunov exponents, entropy, all the concepts that are associated with the deterministic case. They continue to make sense. You're not iterating the same map, you're composing different maps, but you can continue to capture the same things. And importantly, these are non-random quantities. They don't depend on the realization of the path. Okay. So now, going back to this ideal picture for deterministic systems. Okay. First, that says that if I transport Lebesgue forward, it converges. Okay, we've already gotten that in the random case, but it says more. It says that if you push this forward, it's either a sink or it's an SRB measure, meaning that it's smooth on unstable manifolds. So I'm now going to show you a theorem that says exactly that these things are true in the random case. So given a random dynamical system with stationary measure mu, I have to assume the usual integrability condition in order for the Lyapunov exponent to exist. And these conditions are usually satisfied for SDEs. Then if the lambda max is negative, i.e. if the norms shrink exponentially, then the sample measures are supported on a finite set of points that we can think of as random sinks. This result was proved by Lebesgue in the 1980s. And if mu has a density, so we had, but the average measure is very easy for it to have a density. And if there's growth in norms, then as you push it forward, the measure lives on a random attractor, which has a random SRB measure almost everywhere. And this was proved by Trapi and myself a while back. So random SRB measure looks just like an SRB measure. It's smooth on unstable manifolds. But now, depending on the history, you're not going to arrive at the same attractor. You have depending on the history, you arrive at a history-dependent attractor with a history-dependent measure, which is smooth in its unstable directions. Okay. So this second result was proved indirectly when we did this a while back. We proved it by proving an entropy formula and then showing that this entropy formula, from this we deduce the random SRB property. I hope that going this route is of some interest because it also has the bonus of getting this entropy formula. But then people started to apply this result, for example, to climate science and so on. And I started to wonder, if what I told you about this ideal picture is true, I should be able to prove this directly. Okay? And so I set out to do that. And I gave a direct proof together with Alex Blumenthal. And so this is a second proof of it that doesn't involve this, but involves pushing forward mu and seeing directly that it goes to something that has the SRB property. And the proof, it's really carrying out the ideal deterministic picture that I described to you earlier, except that there is random noise. And when it doesn't work without the noise, with the noise, we show that it in fact is true. Okay. So, and this is, I believe this is what I have for the finite dimensional random case. I could take a couple questions if there are any.
So in some sense, this when you look at the marginal thing, this is like a Markov chain, right?
This is like a Markov chain. Yes, this is like a Markov chain when you when you come.
The randomness comes from the omega, and then the space is the image of the F.
Yes.
Okay.
Yeah.
Thank you.
Yeah. This is like reconstructing the history of a Markov chain, right? And looking at where you are now, given the history. Right?
Yes. Okay.
But and the geometry, and the whole point is that by doing this, the picture is really not that different than for iterating deterministic systems, except nicer. All these unfortunate coincidences go away, and things are nice. Okay, so that's the picture. Okay, so now let me go to infinite dimension systems. I have started from the beginning by saying that Lebesgue measure is what I care about. And when I go to infinite dimensional dynamical systems, there's no Lebesgue measure. So I have a problem right away. And to motivate these ideas, let me first go to a setting when there are finite dimensional center manifolds. I'm going to eventually get rid of these finite dimensional center manifolds, but it's easier to motivate the ideas here. And then I can say it still looks like this. Okay, so let me look at the setting for now of a Banach space, usually to be thought of as a space of functions. And you have a mapping, which is smooth. C1 plus alpha for alpha bigger than 0 is what I need. And this mapping, you should think of this as the time t map of a semi-flow or something like that. Okay, so suppose that I have this setting. And in this Banach space, I want to have a reference splitting. This is just a splitting where things in this two closed subspaces where in EC, you could, in that direction, the map generally can do anything that it likes, but in ES is all contracting. This is a vague notion that I'm going to make precise in a moment. These subspaces are not required to be invariant or anything like that. And then I want to assume that there is an absorbing slab, which basically says that in ES, it really is genuinely contracting. Okay. And this may not be said correctly, but it really is squashing in the ES direction. Now, the crucial assumption is invariant cones. Invariant cone says that if you look at a cone of vectors here, which means vectors that when you project to the ES component is smaller than something times its projection to the EC component. So if you look at these cones, these vectors could be expanded or could be contracted, but it's not contracted infinitely. It's contracted by something that's bounded from below. And in particular, if you look at the vectors in the ES direction, then it's contracted more. But now, this is not the right way to say it. You should be one infinite dimension. One should really back up. Instead of saying that it contracts in ES, you should say that it expands in when you go back in ES. But of course, you can. These maps are non-invertible, so you cannot say that. So you have to say that properly. But one can do that. So conditions, these conditions A1, 2, 3 conditions are satisfied by many equations, such as reaction diffusion equations on compact domains. Let's say satisfying Dirichlet boundary conditions, or Klein-Gordon, and many other situations. Okay. So there, you could think of this as a existence of a central manifold, perhaps a global inertial manifold, or just a more locally defined central manifold. Okay. This is the type of situation that it applies. Now I'm going to tell you about, and so these assumptions are assumed in the next 10 minutes or so. And I'm going to state 3 results. The first one is very well known. The second one, also well known, but a little bit less. And the third one is perhaps lesser known. And the third one is what I really wanted to tell you. But I have to start with the first to set myself up. So the first result is the existence of a center manifold. And this was proved by Konstantin Voyage, Nikolenko, Chow, George Sell, Malay Perret, many other people, a very long list. And what it says is that under these conditions, then there is a graph from EC to ES, which is as smooth as the map. And this graph is invariant. Okay. So, and that's called a center manifold. And I think everyone knows that. Now, the second result, which is also known, and I had trouble figuring out who did it for the first time, but certainly not me, because it's been known for a while. Let me show you the picture. So the second result says that there is a stable WS foliation. So in this picture, I didn't, these are the subspaces EC and ES. I did not bother to draw in the central manifold because I don't care about that there. But what it says is that there is a WS foliation described by the green lines. And remember, this is an infinite dimensional space. So these manifolds are usually infinite dimensional, possibly finite codimension, but infinite dimensional. And these manifolds are equivariant in the sense that when you apply the map or the flow, you carry one of these to another one. Okay? So they move, the dynamics would move these things around, but they carry whole stable manifold to whole stable manifold. So you have a whole foliation like that. And if you look at the dynamics along each leaf, usually infinite dimensional leaf, then you see some asymptotic contraction. So this is the second result. Now, the third result is the one that I wanted to tell you, is the absolute continuity of the WS foliation when the center direction is finite dimensional. So this notion of absolute continuity showed up once before, but let me now say this carefully. So if I take 2 disks, sigma 1 and sigma 2, they are transversal to the stable foliation. So think of them as having the same dimension as the center manifold, but any 2 disks that are transversal to that. Then you can take a point and slide it along and define a holonomy map from one of these transversals to another one. And the conclusion, and this is what requires C1 plus alpha, the other 2, C1 is fine, but for this result to hold, you need a little bit more than C1. And what this result says is that as you slide from, so sigma 1 and sigma 2 are finite dimensional, so they have a notion of Lebesgue measure on it. And what this result says is that the mapping, the holonomy map preserves the Lebesgue measure class. It takes the positive Lebesgue measure sets to positive Lebesgue measure sets, 0 Lebesgue measures to 0 Lebesgue measure sets. And this is true for all sets. Okay. So now let me interpret these results for you. The picture is like this. In this picture, I'm still assuming this condition, center manifolds assumption. Here is a finite dimensional center manifold and a finite codimensional foliation of stable manifolds. Okay. Now, the existence of the finite dimensional center manifold it's obvious, everyone knows that. It means that even though the dynamics occur in infinite dimensional space, it is very finite dimensional in nature because everything gets contracted towards this finite dimensional object. And now the existence of a stable foliation says more than that. It's more than just things becoming asymptotically close to a finite dimensional object. It means that if you start from any initial condition, there's actually an initial condition on the center manifold that is going to follow, and it's going to follow exponentially fast. So that means that if you know all the solutions on the center manifold, then it's going to describe all initial conditions everywhere, because each one is going to follow exactly one of these conditions, and it follows that exponentially fast. Now, the absolute continuity of the stable foliation says even more than that. It doesn't just follow it. It says that if you take any other finite dimensional manifold that's transversal, that let's say has the same dimension as WC and is transversal to the stable manifold, then the Lebesgue measure class there corresponds to the Lebesgue measure class on WC. Okay. Now, so what this says is that if the second one already tells you that all the solutions can be in some ways are described by everything on WC. Right? WC is invariant, and all the solutions on it describes everyone is going to follow one of those. So what this says is that what if I collapse all of these leaves? In other words, I'm going to quotient out all the initial conditions that are going to become exponentially close. If I quotient that out, then I would have a notion of Lebesgue measure on this center unstable manifold. Because it's finite dimensional, I have a notion of Lebesgue measure. But in order for this to make sense, this is what is needed. That if you take another slide of something here, that this quotienting out process continuing to make sense if you actually take a piece of unstable manifold up there requires that the notion of Lebesgue class is well defined, and it's equivalent to the one down here, is exactly what absolute continuity of foliation means. So in particular, there's a notion of almost everywhere for in this Banach space. What suppose you have a PDE and you have a k-parameter family of initial conditions. If this k-parameter family is transversal to the WS, which most of the time it would be, then it makes perfect good sense to talk about typical solutions, typical initial conditions and typical solutions. Right? This absolute continuity of the stable foliation is the property that allows you to do that. So another way to look at, so one way to understand this is to say, I'm going to collapse all trajectories with the same future. Another way to look at this is to say observability in the sense of the Lebesgue measure in infinite dimensional spaces can be done via finite dimensional probes. So there's no Lebesgue measure in infinite dimensional space, but you can send in a probe, and look on this probe. That's the finite dimensional manifold that I send in, and I probe it to see if the property that I'm interested in holds almost everywhere on this probe. Now, this idea of using a finite dimensional subspaces, usually is subspaces as probes for infinite dimension, is an idea from classical theory. It's just discussed in a classical book of Benjamini and Lyndon Strauss, and it was rediscovered as a notion of shyness by Hunt, Sauer, and York. And that was still in the abstract setting. What I'm showing here is dynamically, this is very natural, but the dimension of the probes also matter. So if this WC is k dimension and you use a probe that's too lower dimension, you shouldn't expect it to make a lot of sense. But if you use a probe that is at least k dimensional, at least the same dimension of the WC, then because of this property about absolute continuity, what the probe really gives you a well-defined notion of what observability means in the sense of Lebesgue measure. Okay, so now let me go to infinite dimensional systems as defined by PDEs, which is often why we are interested in infinite dimensional systems. So in particular, to fix ideas, let me focus on a class of PDE, very simple class of PDE. Du dt is given by a linear part, and so u is something in a function space, and a is a linear operator, and f is a nonlinear term. Now, I'm about to say something that is very elementary, and please forgive me for saying something so elementary, but because of a difference in culture, people don't usually think of it that way. If you are interested in PDEs, solutions, you look at a solution, you look at what happens, maybe you study the regularity of the solution, you don't really care about a phase space. But to do dynamical systems, you need a phase space. And so you need to fix a function space with a norm, etc. Okay, so this is the first thing that you need to do. And then the second thing is very simple. Of course, you need existence and uniqueness for the dynamics to be well defined. So that's not really a requirement. This is also very mild. You just need the semi-group to be continuous at 0. The last one is the one that one has to be a little careful about. Okay? In order for the dynamical systems to be CR, okay, then it requires that for each T, the flow map be a CR function and be a CR mapping. And that is with respect to the same function space. You have to use the same function space in the domain as in the end. Okay, and this can be a restriction because if you make the norm a little bit too strong or too weak, then it's going to be not so good for you at the beginning or in the domain space or in the range space. And this is something that's a little bit that you need to study dynamical systems. Let me say this a little bit more carefully, that if you one, of course, you need if you want to study a dynamical system, right? But if all you care about are some special solutions, which is often what people care about, or if you want to construct a periodic solution or a solution with this and that property, there's no need to have a whole function space. Okay? And there's certainly no need to have the time T map be CR. Okay? But if you want to study global dynamics, then you need the phase space. Okay? And if you want to, in addition to studying the global dynamics, you want to leverage the geometric differentiable techniques from finite dimension, then this map will have to be CR. Okay? And this is going to impose some conditions on the choice of the function space that one can use. Okay? But here, I want to state at least one theorem to show you that I'm not talking about an empty set. One actually has this quite often, is that so you let X be a Banach space, and A is a sectorial operator, which is another way of saying that it generates an analytic semigroup. These two are equivalent. Okay. Under these conditions, there is automatically a family of interpolation spaces. Okay. So think of this as L2, A as the Laplacian, then is the domain of definition is H2, and there is a whole family of Sobolev spaces in between, but it's much more general than that for any sectorial operator. Okay, so there's a family of spaces with norms that are weaker this way and stronger that way, parameterized by alpha. And there is a theorem here proved in Henry's book in the 1980s that says that if you look at differential equation that's given linear part, non-linear part, if the linear part is sectorial, then you have this interpolation space picture. And if you, for some alpha in between, if the nonlinear part takes that from alpha to X is CR, then everything I wanted to say is true, that the time T map is CR as you see it from this space to itself. In other words, I've found a self-consistent function space where the map is CR, both using the same norm in the domain and the range. But this does put some restriction on. So the way you do it, given an equation, is that you look at the linear part, that determines that, And then you go to the nonlinear part and it tells you which alphas are okay to use in order to get a smooth map. And of course, by solution here, I mean mild solution. So anyway, well, all that I wanted to say here is that the things that I'm telling you about is not an empty set, quite far from it. In fact, with proper choice of alpha, you have this quite frequently. Okay, so I'm going to discuss two general results for infinite dimensional systems. Quickly run over the assumption: X is a Banach space or Hilbert space. Okay, it's a function space usually, and F is a continuous semi-flow. Okay, and I'm going to assume that excluding zero here, of course, it's C2 or C1 plus alpha. I need some backward uniqueness. It's technical assumption that I need to put, but the main thing is that there is an attractor. I need to assume that it's an attractor, so it's in the dissipative category. Think about the very first page, the finite dimensional picture that I'm showing you. I'm going back to that picture, except that I'm now in infinite dimensional space. And a very basic fact is that there is existence of an invariant measure on. This is always true. It's not an assumption. When you have a compact attractor, there's always lots of invariant measures. Okay, so now the picture is I'm now back to my first original picture for finite dimensional systems, and I talked about Lyapunov exponents, stable and unstable manifolds, absolute continuity of stable foliation, and I want to say a little bit about two of these, the first and the third, okay? And then to try to convince you that the things really translate quite well. So F is the same as Ft, it's a time T map for T fixed. Mu is an invariant measure. I want to talk about the notion of Lyapunov exponents. Now, when you talk about Lyapunov, when you look at a finite dimensional operator compared to an infinite dimensional operator, the difference is that there may be a part of the spectrum that one cannot resolve, i.e. the essential spectrum. Okay, so the essential spectral radius is also known as the Kuratowski measure of non-compactness. And for dynamical systems, it's actually, because we're iterating, it's actually easier to use this notion of Kuratowski measure. The two are equivalent, but this is an easier, more dynamical way of looking at it. Is that, so it's defined as follows. You take a map, bounded linear map from X to X, and you look at the image of the unit ball. Okay? Now, if the map was compact, then this object is compact, and of course I can cover it by small balls of whatever radii. But if it's not compact, then if I use a really big radius, then I can cover it because this is a bounded operator. But if I shrink the radius, there comes a point when I can no longer cover it with a finite number of balls. Okay, and this cutoff is defined to be the Kuratowski measure of non-compactness, and it's equivalent to the essential spectral radius for a single operator. Now, in ergodic theory, it's easy to see that if you look at this, because it has a kind of an iterative nature, it's easy to see that this thing is subadditive, and so there's a well-defined growth rate. So there's a notion of asymptotic notion of Kuratowski measure of compactness. And here's the theorem I want to cite. It's been proved a while back, and in fact proved many times over and over because it's a really important theorem by Ruel, Ricardo Magnier, whose work I greatly admired when I was growing up. Philippe Toulon, Lian Liu. It's every so many years someone will come up with a new proof again. So here's an ergodic version of this. It basically says that in infinite dimension, if you take a number which is bigger than this asymptotic measure of non-compactness, okay, then once you take that away, then the picture is very much like in finite dimension. You have these subspaces that are finite dimensional and one that's infinite dimensional. In these finite dimensional subspaces, they're invariant, and you have well-defined Lyapunov exponents. And in the big one where you have bunched everything together, all that you know is that it goes inside of itself, and its growth rate is bounded by this number that you have chosen. So the picture in finite and infinite dimensions are very similar, provided you're able to group together a whole bunch of things that are that are below something a little bit bigger than the measure of non-compactness. Okay. Now, because in the theory that we're talking about, we have to be able to distinguish between expanding, neutral, and contracting directions. So in order to do that, we have to assume that this number is less than 0. If this number is, so 0, less than 0 means contraction, right? So if this number was bigger than 0, then you would not be able to resolve these subspaces. But if the essential part of the spectrum is strictly less than 0, then, well, this part is not completely resolved, but we don't care. We still have a very well-defined splitting. And once you have the very well-defined splitting, then there are local stable and unstable manifolds that one can prove the same way as they are proved in infinite dimension. And the idea of SRB measure also extended to the same setting, because now EU is finite dimension, and so the unstable manifolds are finite dimensional, and so one can talk about Lebesgue measure being the measure having a density when conditioned on these unstable manifolds. And then the theorem that I would like to state says that consider a general setting like this, where F is the time T map of a semi-flow from a PDE, for example, and mu is an invariant measure sitting with an attractor, and mu is an invariant measure sitting on the attractor. If mu is SRB with no Lyapunov exponents, then one can show that the stable foliation is absolutely continuous. Now, this sounds like an abstract theorem, but what it really says is that, well, in the case of a center manifold, we have this picture. This is the center manifold, globally defined, and you have this globally defined stable foliation, and one can and it's absolutely continuous, so one can make sense of the Lebesgue measure. Well, here, this is a generalization of that. The picture is much messier, but locally it continues to look like that. Okay? So locally, these things are all measurable families of stable manifolds, the unstable manifolds, and the stable manifolds also is a measurable family of unequal length and so on. But everything that I told you about this picture carries over. And so in the neighborhood of the attractor, I continue to have a notion of typical trajectories under these conditions. So this is the summary of my talk. In finite dimensions, one often equates observability with positive Lebesgue measure events. Okay. This is what a lot of people take for granted, may or may not fit the purposes. Okay. But under these assumptions, there's a very nice dynamical picture in the sense, in this sense, for deterministic systems. You use the dynamics to carry forward the Lebesgue measure, and it goes to something that's either a point or a periodic point, or it's something that has a nice geometric structure of being smooth in unstable directions. Very nice picture. Unfortunately, is both not always true, and when true, it's hard to prove. Well, then I show that if you add some random noise, then this picture becomes much more tractable and in fact true in the sense that I have explained. So in some ways, if I think of this as a dream dynamical picture, the addition of random noise makes this dream come true. Then going to infinite dimension, in order to interpret one, I lack the notion of the Lebesgue measure to start with, but there's a notion of absolute continuity of stable foliation, which allows one to use finite dimensional probes. Okay? So, and when you have that, and one often does, then the notion of Lebesgue almost every point, Lebesgue almost everywhere, and the notion of typical trajectories would continue to make sense in the sense of finite dimensional probes. And thank you very much. this is the end of my talk.
Thank you very much, Lai-Sang. Very nice talk, really. Is there any question or comment? Sorry, I forgot to thank the speaker.
Thank you.
Okay, while people is thinking about questions, let me ask a question about the random noise. You put an example with the Brownian motion that somehow I lost it because you were talking about continuous discrete time.
Yes.
And then appeared this Brownian motion that is continuous time. So how does it?
If you use in the setting of SDE, then you have you have a flow of different morphisms, right? For each t, you have a time t map, t map, right? You can if you discretize the time for any t, you fix any t, then you can look at it as time t map.
Okay, so you look at
yeah, I'm just looking at that.
Okay.
Yeah, I could actually have set the same things for in continuous time. In dynamical systems, there are always these two versions. One is more complicated than the other, so I took the simpler one.
No, that's fine. But for instance, which example of f w f omega would you take?
Well, there is, it's almost every omega, right? So almost
okay,
every,
but not, but the f, because you cannot, if you change a discrete, it's okay to change the omega, but if you change continuous, you have to change also.
Oh, but I would parameterize. I think of omega now as a realization of Brownian motion.
Okay.
Okay. And
It's
then
like
I look at almost every
Brownian.
omega. Yeah, I look at almost every omega, and actually their behaviors are the same because the dynamical properties are the same because one has to prove that it's not obvious that because they are non-random. But depending on which omega you take, if you run the system for a while and condition on the history, you see something different, right? You see.
Yes.
So you see, yeah. So I think you're very familiar with that in the context of Markov chains, right? So you see something different, but the dynamical properties are always the same. If it's a sink, then it's the same for almost every omega. SRB is SRB for almost every omega.
Okay, so in some sense, you select one of the solutions.
Yeah, and of course they look different, but the qualitative behavior is the same.
Okay.
They have the same Lyapunov exponents, the same entropy, same.
Very nice. Yep. Okay. Are there any other questions? Okay. If not, let's thank Lai-Sang again.
Thank you.
And I think we can finish now. Thank you very much.